So now we move into continuous spatial heterogeneity. And what I'd like to do the remainder of this morning is give you a quick overview of 5 different ways in which one can approach this. And the idea is just to give you a sense of what is out there and some appreciation for the differences between these approaches. As you'll see, several of them are very similar in spirit, and they've appeared in different literatures and sometimes developed totally separately without any cross-citation of any kind, but they all deal with modeling the variability in a more continuous fashion than the discrete regimes allow you to do. So rather than saying a priori the variability is fixed in these subsets of the data, we now let some, if you wish, impose a model for the variability that is smooth changing with space. And the first approach is trend surface regression. This is really the simplest way to deal with what geographers have referred to as spatial drift. Spatial drift is the way in which the parameters of a model change over space. And so then we can think about which parameters change over space. Is it just the mean, which is what is modeled in a trend surface regression, or is it the slope? And then we have varying coefficients, either deterministically, meaning in function of some other variables, or randomly in terms of random coefficients, which we'll see at the very end. So what I wanted to do is start with some of the simple models, and specifically a trend surface, just so you have some idea of what this is. It's a very useful descriptive device. It is not a useful explanatory device because it's the ultimate geographic determinism. If you know latitude and longitude, you know everything there is to know about a phenomenon. So this doesn't actually explain something. I also wanted to bring it in because oftentimes latitude and longitude are introduced in a spatial regression to fix spatial autocorrelation. This is yet another way in which we see the confusion between spatial heterogeneity and spatial dependence. It's the same idea to the extent that the correlation follows a pattern is actually not indicative of a contagious process, but is indicative of what we have called apparent contagion. So in effect, it's really about heterogeneity. Then, indeed, if you introduce latitude and longitude or x and y coordinates in the regression, you may be able to eliminate the evidence of spatial autocorrelation. This is not the same as modeling a spatial process. So it is a fix, just in very much the same way as spatial fixed effects are a fix for some types, some evidence of spatial autocorrelation. I am personally very wary of doing this because latitude and longitude as such do not really explain anything, and they're really proxies for something else. And ideally, you want to know what that something else is rather than proxying it by, location. It's very similar to using time dummies. If there is some effect of time, you don't really know what it is, but you stick in a time dummy which takes care of the problem. So a trend is a polynomial regression where the explanatory variables are powers of the latitude and longitude. The simplest case is a linear trend, which is simply fitting a plane through the data. So the information that provides to you is whether or not there is some systematic change of the phenomenon of interest. In this example, it's the Baltimore house price data set. And so by fitting this linear plane through the prices, so to speak, we can see that the prices go up from south to north and go down from west to east. And that's a very simple summary of the information in the data. And very often this is a useful exploratory device in that it very quickly can tell you something about the spatial distribution of the data. Is this uniform? Is it random? If it's totally random, then the fit of a spatial trend will be very poor. This spatial trend is also something which suggests that the mean is not constant over space, which violates one of our stationarity assumptions. And this is very relevant in geostatistical analysis, which we haven't really talked about much in this workshop, but if you carry out, say, a variogram modeling, then you have to again ensure that the mean is constant and you're always on the lookout for spatial trends. Other trends are higher order polynomials. Second order polynomial, for example, has a parabolic shape and is useful as a summary of phenomena where you have either a core periphery or either a dip in the center or a peak in the center. And you'd be surprised at the, I won't say the explanatory power, but the fit that some of these simple polynomials provide you in a lot of situations. So it's a useful, I like to think of it as a useful exploratory device, which very quickly lets you see, are there some peaks in the data? Are there some valleys in the data? Of course, as you crank up the order of the polynomial, ultimately you have a perfect fit of the data. But that's not the point here. It's more of an exploratory device, and it's also very useful for interpolation because the only explanatory variable, quote unquote, is the location. So anytime you have x and y coordinates, you can have a predicted value. So it's very easy to create interpolated surfaces using a trend surface type of regression. And this is the main application in geostatistics. Geostatistics is about spatial prediction, coming up with values for locations where you have no observations. So if the only variable that you need is the location itself, its latitude and longitude or x and y coordinates, this is a perfect tool to do that kind of interpolation. And what you see very often in Kriging, geostatistical applications of spatial prediction, which is called Kriging, is that the model for the mean is in fact a trend surface, a polynomial in the x and y coordinates, and then the model for the residual or the error term is a spatial model, a model of spatial autocorrelation. So I don't want to make too much of this, but I do want you to be aware that this is a very powerful exploratory technique. It's also very easy to do. Obviously, if you want to get, I alluded to this yesterday, if you want to get really high multicollinearity condition numbers, this is the way to go. Just fit one of these second or third order polynomials to your data and you'll see these numbers go out the window, 20,000, 30,000, like that. So basically what this tells you is, there's no explanation there. It's fit, but it's not explanation, and there's a big difference between the two. So if all you care about is interpolation, fit is good. If you care about explanation, this is not useful, because there is no substantive explanation behind a model like this. Okay, we move on. So the trend surface is the easiest, if you wish. It deals with the continuous variation of the mean. You can think of the trend surface as being a model for how the mean changes with locations in the landscape, if I can use that term. And that's a way to think about spatial drift in the mean. Now we're moving to spatial drift in the parameters themselves. And the first method I want to talk about is this expansion method. There's actually a number of different ways to deal with varying coefficients, and the important distinction is between this method here, which lets the parameters or the coefficients vary systematically with other variables, or with covariates, as I call them. And then the geographically weighted regression method, which is much more of a non-parametric approach to the same problem. It's a local regression or local estimation approach, which actually lets the data determine the variability of the coefficients. So these are two different perspectives on the same problem. Let's say we're looking at a hedonic function. What is the effect of an extra bathroom on the house price? If that effect changes as we move through the city, and in some areas of the city it is much more important than in other areas of the city, one way to model this is to make the coefficient a function of other covariates that may capture this variability. That's the first approach. Another way to think about this is, well, let the data pick it up, and the data will tell us whether these betas actually are constant or change throughout the landscape in some kind of non-parametric way, and that is the approach taken in geographically weighted regression. And so we'll start with the varying coefficients, which is, this is a literature, it goes in and out of fashion, and it's, I would say right now it's pretty much out of fashion, but it's still used by in empirical work quite commonly. The idea is that you start with an initial model, which is this extreme heterogeneity that we talked about. So we have, for each observation I, we have a separate beta I. And then we say, well, the variability of the beta I itself is driven by some other variables, some additional covariates. And these are the z's. So beta I is itself a function of, say, z1 and z2. And this is called, in Cassetti, Emilio Cassetti is the one who introduced this in the geographic literature. He calls this an expansion equation. So you start with the initial model, which is non-operational because it's extreme heterogeneity. Then you put in a model for the variability of the parameters, which is called the expansion equation. And then you substitute that into the initial model, and what you basically get is a bunch of interaction effects, which then give you the final model. So if you work this out, and this is a very simple example, what we see here is the original constant term. Then we see that the xi beta I has been replaced by an xi gamma 0, which is a straight effect, and then we have the variability. We have the variability with cross product, or the interaction between z1 and xi and gamma 1, and then z1, z2 and xi and gamma 2. So this then becomes the final model that is estimated. You get estimates of gamma 0, gamma 1, and gamma 2. Then you can plug them back into the expansion equation, multiply them with z1 and z2, and you get a map of the beta i's. You get a separate beta I for each location. So we have, quote unquote, solved the problem of extreme heterogeneity by modeling the heterogeneity in an auxiliary regression, this expansion equation, which relates the variability to specific covariates. And the initial application of this used a trend surface for these covariates. So you had a model, an initial model, then you stuck in a linear or cubic or whatever trend surface for the parameters, which fit the variability of the parameter to their location in space. You substitute that back in, and then you can make a map that shows for each location what the parameter value would be. You had a question still?
In time series, some version of this allows switching of the signs of the coefficients or something like that? I'm trying to remember how that works.
There can be a switching of the signs depending on the z's. So it's driven by the second regression, by this relationship. Okay. So the interaction effects, they come out. I mean, you actually don't estimate this. By substituting it into the equation, you get all these interaction effects. So then you get certain gammas, and if you plug these gammas in here, depending on what the z's are, you could get positive or negative betas. Okay, but it's this relationship that drives the sign of the betas. And then you can make a map. So as you will see in the lab again this afternoon, this is actually fairly easy to implement in R, because R allows you to do interaction, create interaction variables on the fly. You don't actually have to compute them separately and then stick them in there. So here we see an example of what a spatial expansion model would look like. It's a very simple example, again using the Columbus data and allowing the parameters to vary linearly with x and y coordinates, which is about the simplest way you can implement this. And then you see in the inc x and inc y, these are the interaction effects between the different parameters. And what you see in this regression is that there's very little significance in terms of these interaction effects. That's just the nature of the example. So then the actual use of this is let me move forward, is something like this, a map of the parameter variability. And I show it to you here because what I'd like to do is keep this as a running example, and then I'll switch to the geographically weighted regression, and then you'll see the difference or the similarity between the two. So this is the kind of parameter variability that you see, and essentially what it's telling you, because it is a linear trend, you will see patterns that are north, south, east, west. And what it's telling you, you can think of a kind of a plane that starts low in the northwest corner of the city and just kind of tilts up towards the southeast corner. And so the parameter value of housing value in the regression of crime starts small in the northwest and increases towards the southeast. Okay. So it's very simplistic, but it's very easy to make this more general and to introduce other covariates. They don't have to be latitude and longitude. They could be other parameters. The practical problem with these types of models is because of all these interaction effects and these multiplications, you tend to get a very high degree of multicollinearity. So some of the work on the expansion method, this is, mostly in the 80s, has focused on what to do about this and using principal components or other techniques to get around the problem of the multicollinearity and to still have these interaction effects and be able to come up with maps of the parameter variability. So in terms of practical implementation, there are some issues here. Again, I like to think of this as a very useful exploratory technique where you very quickly get a sense of how strong is this and how viable is this assumption of stationarity, of one size fits all. And in fact, because it is a regression model and because you have standard errors, you can actually carry out tests for the significance of the variability of the coefficient, because you can test in the, if you think of the expansion equation, it has beta I as gamma 0 and then all the covariates. So you can test on the significance of these gammas. And if they are in fact 0, then there is no variability, and then you have a fixed coefficient. So it's another way of thinking about testing for homogeneity, based on the standard errors of a regression. Before the break, we had the regime, so we pooled everything together and also estimated separately. Here, through this expansion equation, we get to the final model, and we can test specific hypotheses, zero constraints if you wish, on these interaction parameters, and if they are not significant, then there is no interaction. Then you have a constant coefficient.
Can I take you back a slide to the table? Just make sure.
This one?
Yes,
Yeah.
make sure I get this. So you would take the income X and the income Y, and you're plugging those into the final model to get the gammas 0, gamma 1, gamma 2?
Yeah, well, the ones without the interaction effect are the constant parts of the parameter. So the gamma 0. And then the gamma 1s and the gamma 2s, which are the interaction effects, are the parameters of these cross products here.
Okay, and just in this example, you've got an x and a y that you're putting on the, you got,
Yeah. It's just simple latitude, longitude,
yeah.
right? But there are several applications of the expansion method that use other covariates as well, and not just, for example, variables to capture neighborhood characteristics. So then you would run a hedonic type model, and you let the parameters of the model vary with neighborhood characteristics. And then again, the null hypothesis is they don't vary, they're constant throughout, and this is a testable hypothesis. Where it gets tricky is because of the multicollinearity, these t-tests tend to be unreliable. So therefore, there was a lot of interest in getting rid of the multicollinearity through the use of principal components or other techniques to get around that problem. But it's, this is not rocket science. This is very, I like to think of this more as an exploratory technique. If you find that, in fact, these parameters are not constant, that should be a red flag. Why are they not constant? What is it that we're missing in our specification? So then a slightly more complex form, and the reason I introduce this here is I just want you to make a mental mark and hold this, and then later on when we get to the random coefficient models, you'll recognize a lot of similarity. And these are all models that eventually are models for heteroscedasticity of one form or another. So the what I call the random expansion model, rather than having a deterministic expansion equation, which is the beta I as a function of other covariates, we introduce some random term in there. And that, in other words, we get around the deterministic variability of the coefficient, but we make it consist of a deterministic part and a random part. Okay, later, when we deal with random coefficients, it will be only a random part, no deterministic part. But we'll see that basically the problem is the same. If we do this substitution, because of the interaction effects, because of the cross products of the z's and the x's, and because of the cross products that follow from the expansion equation, we have an error term that is also multiplied by the x's. And because of that, it will no longer be constant. This is a standard form of heteroscedasticity. So the combined error term that contains both the part of the error that we get from the expansion equation and its interaction and the original error, if we take the variance of this, assuming that these two parts are uncorrelated, which is a standard assumption, then the variance of this x part is non-stochastic. So it's the variance of the psi times the square of the x. And the square of the x changes with I, which is observation. So it is not constant across observations, which is heteroscedasticity. So that's a classic model for heteroscedasticity. So then, if you really want to do it right, estimate these expansion models correctly, you should allow for heteroscedasticity of this particular form, because the model tells you this is the form of the heteroscedasticity. Next, there's 5 of these. We're halfway through, almost halfway through. Multi-level models. Multi-level is yet another way of dealing with heterogeneity, but now, and it's in spirit, it's similar to the regimes, but it only works if you have data at multiple levels of observation. So in the regimes, if you wish, we had data at a small level, at a micro level, but we cut the data set into subsets. We didn't have any data at the subset level. Okay, so we had the South and the non-South, but we didn't have additional variables at the whole aggregate South level or the aggregate non-South level. In a multi-level model, that is a requirement. So you need to have data at multiple levels of observation, and you have multiple levels of explanation. A lot of this research comes out of the education field, educational testing. So you test students in a class on some kind of aptitude or performance test. Then you're interested in finding out, well, how much of this is because of the student, how much is because of the teacher, how much is because of the school superintendent, the school district, the neighborhood effects, and so on. So you just scale up. And this also lends itself very nicely to spatial analysis if you have data at multiple levels, and say you have county data and you have state data. And then what you're interested in is explaining the variability at the state level for the regressions that you carry out at the county level. And then you get, depending on how complicated you want to make it, and I'll show you some examples in a few minutes, you get very complex interactions in the error terms. And the actual terms of the model themselves are pretty straightforward, but the errors have highly complex covariance structures depending on how much interaction you allow, both at the individual level or at the aggregate level, or crossing between the two. And I'll show you a very simple example. Let's just think of this of units I, say counties, within a region J, say a state. Okay. And then each region, each state, we allow it to have a different parameter. This is just like the regimes. Our model is not at that level. The model is at the individual level. So the model, this would be a county model with some variables that are, county specific, and some parameters that are state specific. So we have Yij, meaning county I in state J, has its own intercept specific to the state J, has a slope, beta J, specific to the state J, and then an error term. And we're letting the slopes vary across the groups. So it's similar in spirit to the expansion methods, where again, we let the slope vary. In the expansion method, we let it vary as a function of specific covariates, specific additional variables that we introduced. Here, we let it vary as a function of additional variables, but these variables are at a different scale. In the expansion method, the z's that we introduced would also be at the county level. Here, the z's are at the state level. So let's say we have a county model for crime, and we allow the effect of, say, income or employment, let's say employment, to be different in each state. And then we have a model that